So notice you're seeing like a lot of places it intersects, and we want it from 0 to 5, which means you might want to adjust your window, because you're seeing from 0 all the way to 29, which means pi is like 2 times 3 is about what? Pi is like 3, so it's 2 times 3. So like we only want between 0 and like 6-ish, right? And so we're like not sure where 6 is, we don't know how many of these like end up being. So if you go to your window and you adjust it, maybe say like between blank, I don't know, we don't want to really start at 0 just because then you can't see what's happening at 0, so it's there's still a little bit of wiggle room, like -2. Once I'm reading, let's go up to a little bit past, like 6-ish, like 7. So now notice it's going here and here. So those are the points that we want to find. So see, we go to menu and analyze graph, and there's these little intersections. Find any? There's a point here on the green for reading. Yes, but notice it says between 0 and 2 pi. So we don't want anything over here on the negative side. And we only want to go over to around like 6-ish. So let's adjust your window a little bit to just see the ones that we want. So let's maybe say like instead of going all the way over to like -10, let's go to like -2 so we can at least see 0. And then maybe not as far as 7 because 2 pi would be like 6-ish, right? So like maybe like 7. 2 times 3 is like 6. So we only want to find these points of intersection. Not the ones over there. But yes, what you were doing is correct. The inner one. How are we doing over here? Okay. So, did you graph these two? Just right there. I'm going to find where they intersect, so you have to see the graph. Depends on kind of like what your windows are at, when you graph it, whether you can see it or not. There you go. Did you get it? Did you sum it algebraically or did you graph it? Did you divide by a sine or a cosine? Oh. Okay, so be careful when you divide by sine. It's kind of like when you divide by x. Or when you divide by a variable. Like, so we're going to learn another way algebraically, like without dividing by you're getting some of the solutions, but you're going to see so when you go and you graph it, you're going to see it crosses here on this side, and it also crosses another side. Okay, so you're close. And there. Okay, so yeah, so you can like not seeing the line, which is getting slightly wrong. So I don't know if you So then if you go here and you only want to see between 0 and 2 pi. Instead of saying 0 here though, I want to say like -2 because I want to see what's happening at 0, and if I see 0 it's like there where it's hard to tell. And then 10 is okay, 2 pi, let's think about how big that is. 2 times pi is like maybe longish. We have papers. I don't feel this so what's like 3 times 2? Because 6, so let's give ourselves like, like 7 instead of 6, so we make sure we see everything. And we see it crosses here, at 0, and then here, and then here, and we want to find these points. Yeah, that one. Okay. Okay, let's talk about it. Let's talk about Pi Day is March 14th. It's during our spring break. So we'll have to celebrate another time. Okay, so here we go. I wanted to include this problem because I think sometimes we don't do like as much calculator work, and when y'all get to a calculator section of the test, there's a lot of times where you can actually solve equations, like we're going to be doing today, solving trig equations. Another option of how you could solve your trig equation could be by graphing the two sides and seeing where it intersects. Because think about it, yesterday we did the types of problems like this, right? 2 cosine x plus 1 equals cosine x or something like that, right? And algebraically we like moved cosine over and put the cosines together and we found cosine equals something, and then we looked it up on our unit circle. If you're on a calculator section and you feel really comfortable on your calculator, you could always graph this one and see where they're equal or where they cross, and those would be the same x values as you get when you solve this that we did yesterday, okay? Now today, if you try to set these two equal to each other algebraically, so set this up because we're going to do it in a second, 2 cosine x sine x, we want to know where it intersects or is equal to 2 sine x. See how what intersect means, like where they're equal? So that's what we're trying to solve, but what's different about this problem than the problems we saw yesterday? Has two trig functions, cosine and sine. And so if you try to subtract 2 sine over here, these are not like terms. We can't just like take it away from this sign because this sign's attached to cosine. And so that's like a family we can't break up yet. And so we got to figure out another algebraic strategy. So we're going to come back to that. That's what we're going to be kind of learning and focusing on today. But first, let's talk about what we found on our calculator, because we should get the same answer as we're going to get when we do this algebraically. So let's see what we get. So when you graph this on your calculator, let me pull up my graph from the last class real quick. There it is. I got these two graphs right here. This is where's my cursor? There it is. This one is the 2 sine cosine, and this one is the 2 sine, no, opposite. I don't know, actually. But anyways, we see them graphed. We see that they cross here and here and here. Some of y'all maybe had a window that was zoomed out a lot more, and you saw they crossed a lot of places, right? But remember, we have an interval. It says between 0 and 2 pi, okay? So if you adjust your window, we went between 0, which is the y-axis, all the way to like 6 point something, because 2 times pi, which is 3.14, would be like 6-ish, right? Okay, so we see 3 spots. I used my little intersection tool, and I found that this spot in the middle is like 3.14 something, something, something. Does that sound familiar? What's 3.14? Pi. So this is the decimal version, but this is actually saying that one place that these cross is at pi. If you go ahead and you do this one over here, did anyone do this one, this intersection? What'd you get?
I mean, because when I tried to do it on 2 pi, it would like say there's nothing, so I had to like do it.
Yeah, you have to go a little bit past exactly 2 pi, or it's like on this line and you can't click right there.
So I didn't write it down because I thought.
Okay, cool. So if you go a little bit further to 7, did anyone, or 10 or something like that, a little bit bigger than it, you can actually find this intersection. Anyone get to that part? You end up getting 6.28 something. Yeah? Is that what you got, Anthea?
Yeah.
And what is 6.2? That's 2 pi. So we end up getting pi and 2 pi, and then visually you can kind of tell that this one is crossing at 0. If you do it on your calculator, you might get a really, really small decimal, like 1 point something e to the -8 or -9. But when you have something to like a -8 or -9, that's like a really small number, very close to 0. And your calculator's just doing that because calculators kind of like round and are doing some interesting things when they're calculating intersections, and so they're like slightly off there. So we got 0, roughly, pi, and 2 pi showing up on our calculator. So those should be our solutions between that interval of 0 and 2 pi when we solve algebraically. Okay, so now the goal is, can we figure out algebraically how to solve this? Now, Ihong, I saw kind of started, and I saw a couple people in some other classes trying this today. what did you try to do first, Yuhong?
Divided by 2.
Yeah, so good idea. Like you just got rid of the 2 divided by 2 on both sides, and you get cosine x sine x equals sine x, right? And then what'd you do?
Divided by sine x.
Okay, so he noticed that if he divided by sine, he got 1 over here. And when you divide by sine, that like cancels out the sine and you'd have cosine over here. Now you gotta be careful. This method is going to, you're gonna lose some of your solutions. He only got 0 and 2 pi, he didn't get pi. Because when we divide by sine and like magically make sine go away, we lose some of our solutions of where sine could have been 0. And so what we're going to use as our strategy is we're going to try not to divide by the variable that we're like solving for. In algebra sometimes y'all might have talked about that you can miss some solutions when you divide by x, the value that you're solving for. So we want to be careful when we're doing that. But that's a good idea as we're trying to think of things to get started. What we want to try so that we don't get rid of the sign is the strategy we're going to learn today is kind of like how to factor or set our equation equal to 0 and then use factoring to help us. So what I'm going to do is I'm still going to subtract sine over to this side. I just can't combine them yet, but let's see what happens when I subtract sine over. So I have cosine x sine x minus sine x equals, and if I subtract sine, now on this side I have 0. Do we see how that's equivalent? I just moved the sign to the other side algebraically. Okay. The reason that I'm still going to move it to that side is I can factor this now if I look for common factors in both terms. What do both of these have in common? Sine. And so anytime I see a common factor, like if I see 2x plus 2, I could factor that 2 out front and say 2 times x plus 1. And you can distribute this back and get 2x plus 2. You can go back and forth between factoring out a number and then distributing the number back in, right? So we're going to pull a sine x out front and see what's left in each of these terms when we do that. If I pull sine x out front, what's left in this first term? Cosine of x. And if I pull sine x out front, that leaves behind like a -1, right? So sine times cosine is our cosine sine. Sine times -1 is that minus sine. This is equivalent. Sine times cosine is cosine times sine. Sine times -1 is our negative sine, if you distribute it back in. We did the opposite of like the distributive property, we factored out the sine. Happy? Okay. So, no? Well, maybe not happy, but understand?
Yeah.
Okay. Stop me if not, because if you're like, factor out, what does that mean? Like, I can kind of like go over that, because we're going to do it a lot today, so we need to understand what's going on there. Okay, so then, the cool thing about what factoring helps us with is what it shows us is that if this is equal to 0, I've got something times something should give me 0. If something times something equals 0, either this is 0, or this is 0, or both of them are 0, right? That's the only thing that makes sense. So anytime you factor and it's equal to 0, it's helpful because I can break this into like 2 separate problems now and say either sine of x is 0 or cosine x minus 1 is 0, right? Those are the 2 things that would make that equation true. And now we go ahead and we find the angles where that happens. So sine of x is 0 at, that's y is 0 here and here. So we're at 0, right, at pi. And you can look at your unit circle, but I'm trying to remember them more than like just looking at the unit circle over time. So it's 0, y is 0 again at pi. And then since we've got to go all the way around a full circle from 0 to 2 pi, it's going to be back at 2 pi. It's going to be 0 again. And you have to list both 0 and 2 pi because those are 2 different angles, right? Even though they're in the same spot on our unit circle. Looking at your unit circle, take a look at 0. See how it's 0? At pi, it's 0. And then at 2 pi, which is in the same spot, it's at 0. Yeah? Okay. Now let's look at this one. I gotta add the 1 over, and I got cosine x equals 1. let's think about where that happens. Cosine, our x value is 1, only right here, right? But again, that's two different angles, 0, and then all the way around the circle, 2 pi. 0, and 2 pi. So if I were to list all the possible x values putting this together, I don't have to list 0 and 2 pi twice, because they show up in both. But I need to list 0, because that shows up. I need to list pi, because that shows up. And I need to list 2 pi, because that shows up. And I end up with the same spots that we said we got on our calculator, right? 0, pi, and 2 pi. Now when you divided by sine, when Nihong divided by sine, or that strategy we were talking about before, we get that cosine equals 1, you get this piece, but we don't account for the fact that sine could also be 0, and if sine was 0, these would also be equivalent, right? And if sine is 0, you're going to have that angle pi that you would be missing if you didn't have that piece, okay? So our strategy is going to be to set the equation equal to 0 by moving it over. Factor out anything that you have in common so that you can separate it into these two separate pieces. Okay? Alright, so taking that strategy, let's see if y'all can do it. So flip the page. I'll let you do this one with your neighbor since it's the first one you're trying after our model. So flip the page and you'll see this example right here, which you can use a similar strategy to the one I just modeled. So try it out. And then we'll come back and check it. Go. Thank you for waiting. Yeah, subtract the 1/2 cosine. Move it to the other side to set it equal to 0. It's just like saying like 2x or something, like 1/2 cosine is just a number. Okay. So you can't actually subtract it from cosine. I mean, that's fine, you can write it there, but just because you put it under this cosine, you can actually subtract these. You're just going to write in the whole long line, because this one's the cosine sine. What did I have in common with that? We will have cosine, right? So that's what we're going to factor out first. We're going to put cosine in front of the parentheses. So cosine times in parentheses. What's left in the first piece? Okay. So -1/2 plus. Yep. Yours is going to be sine minus 1/2 right here. You did it differently. So your first term will be sine. Got it? Yeah, typically there's an x in the anytime you have second cosine. Okay, so now you get these being multiplied. This is 0, and then negative is 0. This is 0. So it's put into two separate problems. He's with us. Just put now separated into two separate columns equal to 0. Like what? Oh, here we just these two pieces. So here just these pieces. You said either sine x equals 0. What the heck is this? Equals 0 or cosine x minus 1 equals 0. Right? Because if I have something times something, this is multiplication, right? If I have something times something equals 0, the only way that it could, my product, my answer could be 0 is if one of those things was 0, right? Like this could not be 1 and 5, because 1 times 5 would be 5, right? Like I need one of these to be 0 to give me 0 over here. So I'm going to take these and set them both equal to 0 and see what they do. Okay? Right. Great. So now this separates the times something times something else to get me 0. Either this thing has to be 0, so let's set that equal to 0, or this thing has to be 0. And now you get two separate problems.
Mine is cosine.
Oh wait. first thing we did on the other side. Flip back. Remember we said we tried to divide, we forgot about it. So that's what Ehong tried, but he didn't get all the answers, so we decided to do the same answer. But we divided by the 2, then we subtracted the sine over. So here you can subtract 1/2 cosine x over the other side. So this is the cosine x minus 1/2 cosine x. You can't put them together. You just move it over. Because you can't put these together. These are not like terms. This is like you're x, y, minus 1/2 x. Like you can't, those are not the same type of term. You can't put them together. So you don't, I mean, you can divide by the half from the beginning. In this case, I would leave the 1/2 with it. Because like, I don't have a 1/2 on this side. The only reason he divided by 2 is because this is on both sides. I would just subtract the 1/2 cosine x over the other side. Well, that's true, but then you gotta split it by 5, right?
I'm trying to explain.
Get it where like I understand. On this one, our first time was divided by 2.
Everybody's struggling.
So did you multiply all by 2? Yeah. That's what both sides by 2. Okay. So then you have 2 of these, but this is, what this means is about 2 times this stuff. So not just 2 times sine, right? If you have 2 times, this is the subtraction sign. Great. So like, that's fine as long as it's the same multiplication. Minus cosine x equals 0. So then, when you pull out a cosine x, you're just left with 2 sine x minus 1. Like this, right? Do you see that? Okay. So then either, anytime, let's keep this equal to 0 because that's key. Whenever I have multiplication and my product's 0, then either this had to be 0, right? Or this had to be 0. So we're going to split it into 2 separate problems now.
I'm good.
Okay. And then you're going to solve this one, add 1, and then divide by 2.
I'm not going to sleep. I'm not going to send you any more requests anymore to me on my games. You just go first.
What game?
I'm more friendly.
Okay, what'd you do first?
Think about the first.
Airplane making?
Is he divided by the 2? Is it this? Okay, he did that because it's like nice because it was on both sides, so it just cancel out. In this case, it doesn't really help a whole lot. I mean, you can. Last year I thought of something else clever, which was to multiply both sides times 2, because that just makes this 2 cosine sine, and 2 times a half would cancel out the half. So if you really want to get rid of the half, you can try that, or you can just leave it there the whole time and it'll be fine. Okay, so now the goal is, remember, to set it equal to 0. So we're going to subtract cosine to the other side. Right? And then now you're looking for what they have in common, which is cosine, and you're going to try to pull that out front to factor it. Yep, that's fine. Yep, this is good. But cosine
There we go.
is not 0 here. Cosine is 0.
Now I fixed it.
Cosine's x. So like, let's think about it. You said that cosine is x here at 0, and that's not true. This is your point here. Like, cosine is 1 here. It's here. Okay. Okay, so cosine x equals 0, because like when you have it in this form, we want something times something equals 0, because when it's equal to 0, then one of those two has to be 0. If I said something times something equals 6, it's like 2 equals 3 or 61. But 0, it's easy because the only things that give you 0 is 0 times the number, right? And so I'm going to set cosine x equals to 0, because that would cancel the whole thing out, so make that 0. And I'm going to not set sine x, but I'm going to set the whole thing of sine x minus a half equals 0. Does that make sense? And then finish solving. What we got?
We got number, we got limit, we got
The cosine that we're taking out is just one cosine.
Like each of these angles came from within.
And then it's cosine minus 1.
Because at 0 degrees, at 0 degrees, cosine is 1.
Right, 1/2. So that's 30.
So these were pi over 2 and 3 pi over 2. At the top and the bottom, cosine is 0. And then sine is a half of pi over 6, but it's a half somewhere else. Okay, we're going to take a look, see what we think, because then we got to go on to a few more different strategies as things get a little more complicated. Okay, bring it back, because like I said, I'd love for y'all to be able to do your exit ticket here in class and 100% at home like I did with class. So we ran out of time. Okay, remember the goal again is to set it equal to 0, factor, so that you can split it into two separate things. I'm not going to go through all the steps. If you were struggling on this one, I'd be happy to kind of one-off with you as we move on. But to kind of speed up the process, I'm going to skip to the very bottom where you should have had the actual trig functions all solved. When all was said and done, you should have had cosine x equal to 0 and sine x equal to 1/2. And you're getting your angles from both of those. Okay? So if you lost track kind of somewhere along the way, then kind of call me over and I'll help you out. So cosine is 0 at the top and the bottom of the circle. Cosine is 0, because that's our x, right? So that's pi over 2 and 3 pi over 2. And then sine is 1/2, that's your y, here and here. So pi over 6 and 5 pi over 6. Okay? So all 4 of those would be our final answer. Pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. In any order, but. Okay? Y'all can keep your voices off. If you have a question, you are welcome to raise your hand, but I'm going to try to keep this moving, so if we could keep those voices off. Is that a question? No questions? Okay, good enough. Okay, so here's a summary of where we've been so far with solving. And really focus in here to kind of my thought process of your strategies. I think for a lot of y'all, proving was difficult at the beginning of this unit. So I really want you to feel confident with the solving problems, because one, if you can cruise through these and feel good on them, it's going to save you more time for like the proof type problems on your quizzes and your tests. And then also, if you don't get any of the proofs like on the test, you get stuck on a lot of them, like you can still get a lot of points from your solving questions, okay? So I want you to feel comfortable with this kind of half of the unit as you continue to get better with your proving. So here's my line of thinking when I see a problem that says solve. I'm not trying to prove that this equals this by like substituting things in. Last year I saw some people that started to get confused with the instructions and they didn't know like when they were moving things over and when we're like taking a side and doing all this stuff to get to the other side, right? That's when we're proving. So it says solve. When you see solve, we need to be thinking first, if it's a problem like yesterday where we have just cosine or we have just sine and neither of them are squared or anything like that, those are all like terms, then we can combine them together and just solve. Yesterday we felt really good. It was a short day. We cruised through our practice, right? Okay. If trigonometric functions cannot be combined on one side of an equation, then our brain needs to go somewhere else. First, we want to see if we can factor and apply the zero product property. That's what we just did. We said let's factor it, so we can say if this times this is 0, then either this is 0 or this is 0. We broke it into two pieces, right? Okay? So if you can't do what we did yesterday, then we're going to try to factor and use the zero product property. Cool? Okay, then if the equation has quadratic form, so we haven't seen this yet, is where we're going next. If we have an equation that looks something like this, ax squared plus bx plus c, so maybe 2 sine squared plus 3 sine plus 2 equals 0. If we have something of quadratic form, then we can still either factor, but how do we factor something that looks like this? The box method from the beginning of the year, so we're about to do a box with our signs and our cosines, lots of fun. Or, worst comes to worst, if your box is not working, you won't see this a whole lot, but you could use the quadratic formula, okay? So those are kind of like all the way down from like level 1, what you're going to start and hope that you have, all the way down to like I'm running out of options, I'm running out of options, I'm running out of options, to like a really difficult problem that you might have to do the quadratic formula for, okay? So the zero product property, just to summarize, is what we did when we broke it into two pieces. We said that if we can prove that a times b is 0, we can get two things that are being multiplied and equal to 0, then either this piece is 0 or this piece is 0. And that's going to help us to break up a sine cosine type problem into two separate pieces that we can actually solve. Or both could be 0. So that's going to help us to solve that part. It's technically called the zero product property when we do that. Okay? The zero product property is also what we're going to do when we do our box method. Because after you do your box, let's say you get x plus 2 and x minus 3 or something like that. That is the same thing as your zero product property, right? Y'all say either this is 0 or either this is 0. So x is -2 or 3, right? Those are the two values that would make these two things equal to 0. So you're technically setting both of those equal to 0. Okay? So that's the zero product property. That's going to be one way that helps us to solve these. If it doesn't, your factoring doesn't work, then you'll have to do your quadratic formula. So just to remind you, because it's probably been a while since you saw it, it's that song, -x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Nice, good job, y'all. So you want to write that down? I'm going to do plus or minus because I couldn't figure out how to type plus or minus, so I just left a little gap. -b plus or minus square root b squared minus 4ac all over 2a. Realistically, if you like the box method, I mean, you could always use a quadratic formula if you want. Omar likes a quadratic formula, and in the last class I had him quadratic formulating all the ones instead of doing his box method. So if you want to do that, you can. But realistically, you won't see many where you have to use it. Most of them are going to be able to do the box method. The box? Quadratic works every time. Every time. Just takes some square rooting and some funky stuff. Okay, so let's look at an example. And I'm going to walk through this thought process, and it's going to get us to one of these like last strategies that we haven't seen yet. But let's also talk about why we can't do the things we've already done. So, the next problem says, find all solutions to the problem. 2 secant squared x plus 5 secant x plus 2 equals 0. So if I look at this, I'm thinking first, like yesterday, can I just combine things to get secant equals something? I have secant and secant, but can I add 2 secant squared and 5 secant squared and say like 7 secant? Those are not like terms because one is squared and one is not, just like x squared and x. You can't put those together, right? Okay, so shucks, I can't put those together, so that means I'm stuck there, okay? Now I think, can I set it equal to 0 and pull out a common factor? Well, it's already set equal to 0. can I pull out a common factor? I see a secant here, I see a secant here, but does this have a secant?
No.
So I can't factor like we just did in the last two examples by pulling out like a cosine or pulling out a sine of every term, okay? Which means this is of our form ax squared plus bx plus c, and we're going to have to do our box or our quadratic formula to solve, okay? If it helps you to replace your secant so that you're not doing a box with like a bajillion secants, if you want to replace it with some other variable and then put it back as secant later, that might be a strategy that helps you out. I'm not going to use x because x is already like in my problem and I don't want to be confused with that x. So you could, for example, call secant for now, let's call it r for Mrs. Rohan, and we'll say that I have 2r squared plus 5r plus 2 equals 0. And that might make that feel a little more familiar when you're doing your box, to be dealing with just like letters and numbers, not secants and stuff, okay? So then we'd say, I'm going to cruise through this box with you to save us some time. We'd put 2r squared in the first box, 2 in the bottom box, 5r out here. And we're looking for two things that I can add up to give me 5r that have to multiply to what? Be careful, not just 2, because there's a number over here. You have to account for that. We have to multiply these. We want 2 times 2 means we're looking for factors of 4. So we're not looking for factors of 2. If you try to do like 1 times 2, that'll never give you 5. So we're looking for factors of 4, 1 times 4 and 2 times 2. Can we find one of those that's going to add up to 5? Yes, what is it? 4 times 1 gives us,
I mean, 4 plus 1.
sorry, no wonder. I saw some weird faces. 2 times 2 is 4. 4 times 1 gives us 4. 4 plus 1 gives us 5, right? So we have 1 and 4. I'm not writing those on the outside. I write those 1r and 4r like this. And now I figure out the outside of my boxes. So whenever you have a number in front, things are a little bit crazier. So I'm going to say, what would give me 2r squared? 2r times r. And I'm going to put the 2r specifically here because I need a 4r here, and I can just say 2r times 2 would be 4r. And here we'd have 1, so that 1 times r is 1r, and let's check 1 times 2 is 2. That works for everything, right? Cool? Okay. So then we end up with 2r plus 1 times r plus 2 equals 0. And now I'm going to go ahead and replace it with secants now that I've factored it. And all my r's, that's what I was calling secant before, so I've got 2 secant x plus 1, and I've got secant x plus 2. And that's what you would have gotten if you kept it as secants the whole way, which you can totally do if you want. I just think it might help some people to change it back now. Okay, we've got something times something equals 0. So what can we do?
Oh, you equal it.
Zero product property. The goal is to get this factored so that we have something times something equals 0, so that either this thing is 0 or this thing is 0. And now we can solve for our x's. So we got 2 secant x plus 1 is 0, or secant x plus 2 is 0. Because what we're trying to solve for is x, right? Our answer should be x equals something. And we're getting closer and closer and closer to getting just x. Okay. Solve for secant, so add 1, subtract 1, and then divide by 2. Secant x should be -1 divided by 2, -1/2. Okay. And over here, secant x equals -2. And you're like looking at your unit circle and you're like, well, I know sine and cosine, cosine is x, sine is y, but what the heck is secant? So if I have secant, which one is related to secant, sine or cosine? Cosine. Cosine is the reciprocal, which means all I have to do is split both of these, and I have cosine, and then I can look that up. So I have cosine equals -2, and cosine equals -1/2. Does cosine x ever equal -2? No. So it's okay for it not to give us any angles. That one doesn't give us anything. No solution. Because cosine only goes -1 would be the smallest we would have, right? Yep.
Wait, so how did you do the first one where you put a half, yeah.
I subtracted 1, I got -1, and I added 2 over here, and then I divided by 2. I just solved this kind of in one step quickly. Okay, good question. And then over here we have x equals, cosine is going to be equal to -1/2 certain places. And if you think about it, it's going to be at the pi over 3's. But if it's negative, it's going to be in like the second and the third quadrant. So 2 pi over 3 and 4 pi over 3? Okay. On your paper, what do the instructions say about our interval? All real values. Remember how yesterday we wrote that equation? We said either 2 pi over 3 plus 2 pi k or 4 pi over 3 plus 2 pi k. Okay, so that's what you do if it was all real numbers. On my paper, we have different versions for some reason. Oops, my bad. On my paper, what does it say the interval is? 0 to pi, which means in my case, the answer would be not 4 pi over 3, that's too far, right? Mine would be just 2 pi over 3. If I said 0 to 2 pi, it would be both of these. So notice, please pay attention to what it says about your interval, because depending on what it asks, your answer is going to be kind of different. Okay? Cool. Alright, to save you some time tonight, I'm going to actually have, the next problem is one that I had most of my classes do to practice like together, and then they practice one on their own. But so that I can kind of see where you're at and to save you some time tonight, if you want to practice this one at home, I urge you to do so. But what I'm going to give you to practice now is this exit ticket, where there's one like this on the front, so that you can practice it and then turn it into me, so that I can see how you're doing with this. And I'll grade it tonight and get back to you tomorrow. So on the front, there's one similar to this, where you've got ax squared plus bx plus c with cosines. And then on the back, if you have extra time, you can do a proof. So, I mean, in general, anytime they go like this. No, not always when it's 0 only. Because, like, think about it, that's what y'all have done your whole life when you have, can I write them on? Like, anytime y'all do this, we look after, and y'all say 2 and -3, right? That's what you would say your solutions are. It's not just because this is the opposite. What you're doing every time is you're saying, okay, so either x minus 2 equals 0, or x plus 3 equals 0. And if I add 2 over x equals 2, or x equals -3, right? So if this is equal to 0, then one of these has to be 0, because that would cancel it out and make it 0. If you have x minus 2 and x plus 3 equals 6, you can't do that because this could be 2 times 3, or this could be 1 times 6, and you have all sorts of possibilities of equations. Yeah, does that make sense? So anytime you have it set equal to 0, it's nice because you can split it up like that. You can't add those together because that's like 2x squared plus x. You're gonna have to factor it, or do the quadratic formula. So if again you want to call cosine like r and say 2r squared plus r minus 1, that can help you to do your box. Call this r, 2r squared. Just call it like a variable for now so that you can factor it. So 2r squared plus r. So how would you factor something like that? Use the box. Factors of negative 2, that would give me 2k. That's like when we did the whole beginning of the unit with all the proofs. So we have a pile of these familiar table. I'll come around again. Like all the yellow, like all the. Have you done any of your problem set with all the proofs and stuff? Okay, so that kind of stuff, like all the things. Like here you can multiply this, and you know sine, square, plus sine, cosine. Plus cosine squared minus sine cosine. And these are going to cancel. Plus cosine squared is 9.